Okay, I just want to take a few minutes to run through some of the stuff that we need to talk about before the end of the semester. Sorry I can't be there in person to actually do this, but I have been very, very sick, and it's uh, going to continue to be that way, I think, for the next day or two. So I just want to go over some of this stuff and talk about the concepts and maybe run through a couple of practice problems. There are three problems in this note packet. However, I don't anticipate you doing all of them. Some of them are pretty hard, but the first problem is going to be something that you will probably see on the final exam, so it's worth paying attention to. And we'll get to that one once it comes up. Anyways, the first thing that we talked about or that we need to talk about is work. It is the transfer. So the transfer of energy between the system and the environment. So if a system does work on the environment, it is transferring energy from the system to the environment. If the environment does work on the system, say through a push or a pull force, then that is being transferred out of or into the system by the environment. Now, on the other hand, we have this idea of an energy transform, where an energy type is transformed from one thing to another. So we could have something like kinetic energy that is transformed from kinetic energy into maybe a gravity potential energy or a spring energy. In that case, we are basically transforming the energy from one type to another. Now, there's also a lot to talk about with one of those problems that has to do with transferring it as heat versus transferring it as work done. And we'll get to that when we get towards the end here. Anyways, it's important to think about how quickly this energy is transferred. And when we think about this, we are thinking about power. So when we transfer energy, the rate of transfer of energy with respect to time is called power. And the power is basically force multiplied by distance and divided by change in time. So if we have our equation, power is equal to the derivative d dt of the system, the energy of the system. If we were to write some stuff out, maybe say that the energy of the system is actually going to be equal to maybe the work done. Maybe the delta, the change in the energy of the system is equal to the work done. So delta E is equal to work done. And that is equal to force times some distance, which we'll call maybe delta X. So force times distance is equal to this change in energy of our system. But then if we take the time derivative of that, we get d dt of force times delta X, which if I pull the force out, we assume that these forces are going to be constant forces. That is one thing that we can't really calculate power for varying forces. Not with the mathematics that we have currently available to us. So eventually we will be able to do that, but at this time we cannot. So force is a constant, and it comes outside of the derivative, and that just leaves us with d dt of delta x. And maybe you can remember, but this derivative of a position is our velocity. So we would be the force times the velocity would be giving us a power. So the real important equation to take away from this whole entire video is that force times velocity is equal to power. So remember, power is equal to the time derivative of energy. So that is basically energy over delta t, or delta E over delta t. And we had all this idea of energy, or work done, sorry, not energy, but work done is equal to force times distance, right? So this is basically, work is basically, the derivative of work is power. So the unit of power is called a watt, and a watt is equal to a joule per second. That's kind of hard to see because I messed things up there. But a watt is equal to a joule per second, which is also equal to a Newton times a meter. That's a joule. A Newton times a meter divided by seconds. So our SI units of power are watts. So if a force does some work, some external force, like a constant push force, constant pull force, a tension force, anything like that, if it's doing work, It is transferring energy at the rate that depends on a bunch of different things. It depends on the velocity. It depends on the coefficient of friction. It depends on the mass. And it depends on, a bunch of other different variables as well, including like the reaction time, like how quickly the molecules can release heat, things like that. All really depend on the power, or things like that. All cause the power to change or to be something different. So let's say that we have a force that's doing work and it transfers energy at a rate of 5 joules every second. If we want to calculate the power, we would just take that power is equal to the change in energy, which is 5 joules, divided by change in time, 1 second, and our result then is just 5 watts, or 5 joules per second. If a system is gaining energy at a rate of 5 joules per second, we see that the system is consuming 5 watts of power, because that energy that was part of the environment is being taken out of the environment, consumed by this system to increase its potential energy, its thermal energy, or to change some sort of energy in it. Now, if the system, on the other hand, is doing the work, then the system is outputting power. So here, if you probably heard of power output from things like a car's power output, the engine in your car, the engine or the motor, some sort of electric motor maybe, or a turbine or a generator. All these things have this output power because they are a system that is doing something and producing power as a result. So that is, just kind of nomenclature stuff where we want to differentiate between work being positive and being done on a system to increase its energy, which we say is consuming power, versus work being negative, and then a system is doing work on the surroundings, on the environment, and so it's losing energy and work is negative. Anyways, there are lots of different applications for power. You've probably heard the term power colloquially a lot. It does mean a lot of the things that we mean when we say power, but for a physicist, it's a very specific thing. It is a joule per second. And there are some other units, some subunits, or some divisions of the watt that are very important for a lot of different disciplines and in applications in physics and in science and in engineering as well. Those are the milliwatt, first of all. The milliwatt is the same thing you think of, millimeter. It's 1/1000th of a watt. And this is typically used when you have small electric motors. So used in small electric motors or in electronic systems. So if you are talking about circuitry, you're talking about how much power is in this circuit. Oftentimes for our high-tech devices, it's not very much. And so we use a milliwatt instead of watts or larger units. So it is used in small electric motors or in electric circuits. We have nanowatts. These are used in a lot of biology applications. For instance, motor proteins have to do work, right? They have to do work to move an object across like a cytoskeleton or something. So if it wants to move, your cell needs to move some substance across the cell. It can't really rely on diffusion because that'll take too long, and so it uses these motor proteins. These motor proteins have to, exert a force, usually fairly constant force, and it causes a force times a distance work being done, and that takes time. And so, in a lot of biological systems, they will use a nanowatt to describe that power output. We also have gigawatts. Gigawatts are used in larger applications. So used in larger applications. And the types of applications you will see on those are things like turbines, whether it's a hydropower turbine, whether it's a wind turbine, a lot of motors, so like a jet engine would use gigawatts. Even car engines could potentially use gigawatts. Probably be a pretty high-end engine for that, though. Anyways, so gigawatts, obviously these are 10 to the 6 watts, and they are used in these large applications that you see in industrial things. Also for high voltage power lines. just like we used milliwatts in electronic circuits for devices like your phone or your tablet or your laptop. We would use gigawatts for the similar purpose, but in high voltage power lines, because they're much bigger, much more robust. There's a lot more heat energy, a lot more things going on, and a lot more power involved. And so gigawatts are used instead of something like a watt or a milliwatt. Anyways, how much power something is capable of generating depends on how quickly it can transfer an energy. That is that reaction time I hinted at. It depends on the mass. Obviously, the more massive something is, the more energy you have to put into it to get it to move. Internal frictions obviously are going to cause some of your power to be depleted, and the power source as well. So if you're thinking of a system as being your car, then the power source is the engine. And a 1995 Toyota Corolla engine is not nearly as powerful as a brand new turbocharged Lamborghini engine, right? They're very, very different. And so the limiting factor could potentially be the actual engine. Also, you could think about power ratings on engines or on devices that would cause motion. Those are also something that will cause how much power your total system can generate or withstand. There are some other units of power that you've probably heard of that are very common. We have horsepower, which is the amount of work done by a horse. So it is the amount of work done by a horse if the horse is turning a mill wheel with a radius of 12 meters. So this is a very, very old definition. It was actually made by the guy. The horsepower is actually defined by the guy who came up with the watt. Dr. Watt, I guess. But Watt was a physicist and an experimentalist and mathematician back in the turn of the century, 1800s, and he was experimenting and basically said, I think a horse can exert a push force of about 800 newtons. If it were to exert this push force of 800 newtons, it will cause a mill wheel with a 12-foot radius to turn a certain number of times, and that's what we call a horsepower. Super scientific stuff. We also have the British Thermal Unit, BTU. This is the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. So heat required to raise 1 pound of water by 1 degree Fahrenheit. And this may sound familiar to you because there's also this unit called the calorie, which is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. And these two units are very closely related. Finally, there is a foot-pound, and this is the amount of energy transferred to a system. So this is the amount of energy transferred to a system when you apply 1 pound of force over a distance of 1 foot. A linear distance of 1 foot, not a rotational distance. So again, a foot-pound is the amount of energy that you impart to a system when you exert 1 pound of force over a distance of 1 foot. With that, I basically have a couple of other problems I want to kind of work through for you. At the beginning of this video, I had said that the first problem would probably be something that would be fair game for a final exam coming up next week. And the reason why I say that is because it's actually pretty simple to do this. It might not look that way, but once you start to boil it down, it does get okay. Sorry if I have to stop every few minutes and the things seem kind of jerky. It's hard to talk, and I'm blowing my nose and stuff in between, so if the things seem kind of weird, there seem to be some spots where there's like a lot of downtime. I apologize for that. That's just because I'm trying to not drip stuff out of my nose while I'm writing on a tablet. Anyways, first question is, what power rating will a motor need to have to lift a 2,000 kilogram elevator at a steady rate of 3.0 meters per second? This type of problem, the first thing that I would do is I would look at my forces. So step A, look at my forces. And the forces I'm going to see are probably going to be something like a tension force and a gravity force, right? Because we are lifting an elevator. If we draw a picture of that, it is going to look something like, here's our elevator, here's our tension force, and then we'll have some force of gravity pointed down. But the thing is, it has a steady rate of 3.0 meters per second. So this tells us that our acceleration in the y direction will be 0 meters per second squared, because steady rate is the same thing as saying a constant velocity. And again, a constant velocity means we have no acceleration. So again, looking at the forces, I will sum my forces in the in the y direction, and I will have a tension force pointing upwards in the positive direction, and I will have a negative gravity force pointed downwards in the negative direction, and this will be equal to ma. Again, a is 0, so I have T minus Fg is equal to 0. Or T, my tension force, is equal to mass times gravity. So I looked at my force, and then the next thing I need to do is apply my power is equal to my force times velocity. So if I have a force times velocity, the only force that's really outside of this system, because gravity is a part of the system, the only force that is acting externally to the system is that tension force. If you remember, I said that our non-conservative, our external forces are the ones that do not have an equation. We don't have an equation for tension, but we do for gravity. I said we don't have an equation for it, and to find a equation for this, for a non-conservative force like tension, we would have to use Newton's third law and Newton's second law to relate them to conservative forces like gravity. So here we've done that. We've related our non-conservative tension force to our conservative gravity force using Newton's second law. And this is our force F. T, our tension force, will be the same as this force F here. So if I want to calculate my power, I get P is equal to F times B, which is equal to mg, my force, my tension force, times my velocity, v. And we have quantities for all these things. We know that our mass is 2,000 kilograms. We know 9.8 positive. Again, this is positive. I know a lot of people ask me, is it positive or negative 9.8? This is positive 9.8 meters per second squared, times our constant velocity of 3.0 meters per second. And when I plug all this into my calculator, I get somewhere around 58,800 watts. And just to double check our units, we have kilograms times meters per second squared times meters per second. And these two, kilograms meters per second squared, is a Newton. So we have a Newton times meters over second squared. Newtons times meters is a joule. And we know that a joule per second is a watt. And so our units work out great. And our answer, 58,000 watts. So ultimately, to solve this problem, all we had to do was realize that our acceleration was 0, sum our forces in the direction of the non-conservative force. Here, that's our tension force. If this were a horizontal tension pulling horizontally type of situation, this would be a force times velocity in the x direction, and the sum of forces would also be in the x direction if this were a horizontal pull. But since this is an elevator where the pull is vertical, we sum our forces in the y direction. We see that the two forces acting are gravity and tension. We set up our Newton's sum. We relate tension to gravity. Now we have an expression for tension force. And then we apply power is equal to force times velocity. where force is our tension force. We plug everything in, do a calculation, and get 58,000 watt, or sorry, 58,800 watts. Okay, onwards to our next problem. Factory uses a motor and a cable to drag a 300 kilogram machine into place. What power must the motor supply to drag the machine at a speed of 0.5 meters per second? The coefficient of friction is mu k is equal to 0.6. So in the previous problem, we saw a power calculation that we did in the y direction. This was an elevator, tension was in the y direction. Here we're going to have a similar thing, but tension is going to be in the x direction. So if we draw a picture, here's our piece of machinery that weighs 300 kilograms. We want to keep a constant velocity v equals 0.5 meters per second. And there's going to be friction and also this tension force pulling it in that direction. Again, there's friction. This is, we assume that theta here is 0. It's not on an inclined plane. This is perfectly horizontal. And so we don't need to make any assumptions about our normal force being decomposed. So we can basically just say that our normal force is equal to force of gravity is equal to mg. That's something that comes out of Newton's second law. A sum of forces in the y direction is equal to 0, and that gives us n is equal to fg, and fg is equal to mg. So we have an expression for our normal force, but then if we look and we sum our directions in the x, or sum our forces in the x direction, we get ma sub x. Again, we have a constant velocity of 0.5 meters per second, and so our acceleration in the x direction will also be 0. In all of these problems, you will never encounter a situation where the acceleration is non-zero, and so it becomes a little more difficult if it's not 0. But the forces that we see from the diagram I drew on the left here, it says that our tension force minus our friction force, Fk, is equal to 0. And that also gives us tension is equal to friction, which is equal to mu k times n. But we said n is also mg, so we get mu k times mg is equal to our tension force. Again, all this really depends on the acceleration being 0. So we know mu k, we know m, and we know g, and all we have to do now is to calculate our power, is to take P is equal to force times velocity. So our force here is going to be the tension force, which we said is equal to mu k times m times g. That is our force. And then the velocity is still v. Plugging in some numbers, I get 0.60 as my mu k. My mass is 300 kilograms. And my my g constant is a positive 9.8 meters per second squared. And of course, that velocity of 0.5 meters per second. All right, if I plug this all into a calculator, the result I get is something about 882 watts. Right? So not a terribly difficult problem. It's usually going to be, if it's on the final exam, all you will see is these types of problems. One of these two, it'll be either a horizontal or a vertical power calculation like this. All you will need to do is sum your forces in the x or the y direction, maybe both x and y if you have friction. Sum your forces and then figure out what force is causing what is the external force. Usually it's a tension force, a pull force, a push force, that kind of thing. And then putting that all together, you would have P is equal to F times B, where you might need to use Newton's second law to find out what F is, because again, we don't have an equation to describe F, whether F is F push or F pull or tension. We don't have an equation to describe that, and so we have to get that equation from Newton's second law and relating it to a conservative force, or in this case, for question 2, to a dissipated force that we have an equation for, which is friction. So there is one more problem. I think I had a fourth problem in here that I felt was kind of too difficult, too out in the left field to really be useful for us. But this one here is much more complicated than the previous problem. There's a lot of stuff going on, and there's a lot of words, a lot of numbers, and things like that. But if we approach it very carefully and we kind of really take close, small steps, and we're careful about what we do, it should be okay. So in this problem, we have also, I will not expect you to do anything even remotely this difficult on the final exam. Not even close, right? It's going to be first two problems, nothing like this. Okay, so we have a 5 kilogram box. It's attached on one end to a spring with a spring constant of 80 newtons per meter. The other end of the spring is anchored to a wall. Initially, the box is at rest at the spring's equilibrium position, so there's no force exerted by the spring. And a rope with a constant tension of T is equal to 100 newtons will pull on this box and pull it away from the wall, causing the spring to extend. The coefficient of friction between the box and the floor is mu k is equal to 0.3. How much power is being supplied by the rope? So we really need to boil this down to P is equal to F times V, but this isn't going to work out the way we think it is. To solve a problem like this, you really have to start off with your energy equation, your work kinetic energy theorem. So work is equal to the change in energy. And I said in class that change in energy is equal to E minus E sub 0, so energy final minus energy initial. And our E equation is going to be, there might be a potential due to gravity, there might be a potential due to a spring, and there might also be a kinetic energy term, 1/2 mv squared. So the UG term is mgy, U spring is 1/2 kx squared, and T is 1/2 mv squared. We know that this whole motion, the spring or the block isn't going to be lifted up off the ground, and so we can say that y0 and y final are both going to be 0, and so those mgy terms go away in both energy equations. But at the end of the day, when we're done pulling on this spring, we will have some spring energy, and we might have some small kinetic energy as well, because the spring will still be reaching its extended length, or its fully extended length, and when it's reaching a fully extended length, it's still moving, and still there will still be some velocity, but it might be very small. And I would expect that most of our energy in the system at the end will be here in our spring potential energy. So if I write that out, my full energy final equation is 1/2 kx squared plus 1/2 mv squared. My other equation for energy, E sub 0, my initial energy equation, that could also be a spring, a gravity, and a kinetic energy situation. So gravity again is 1/2 mg y sub 0. We said those will be 0 because y doesn't change. U spring is going to be 1/2 k x naught squared, but this is going to be 0 as well. We said that there will be no force initially on the spring because it's at its natural length, and so there will be no energy in the spring as well. And then 1/2 mv squared, which is also 0, so 1/2 mv naught squared, the initial. This is 0 because we are, starting from rest. So if I rewrite this, turns out that the energy final, or the energy initial in my system, is 0. And that makes sense because we don't have motion, we're at rest. We don't have a spring energy. The spring's not compressed or extended, and it's not changing from gravity. And so any energy that's in the system is either entirely due to gravity, which we can ignore because we're going to look at delta E, and those gravity energies will subtract to 0. Or in the absence of this gravity, there is no energy in the system. At least no mechanical energy, I should say. There's still thermal energy and all those fun things. But what we now have is a work equation that says work is equal to energy final, 1/2 kx squared, plus 1/2 mv squared, which is our final velocity, final position, squared, minus 0. So this is basically E minus E sub 0. Now, if we take apart our work equation, we know that this, or if we take apart the work itself, we know that part of that work is going to go into overcoming friction. That means that that energy that would be imparted into the system is going to turn into thermal energy. So what I'm going to do is say that work W is equal to this change in thermal energy, which we'll call E sub delta E sub TH, plus the effective work, or the work due to the external force, which I will call W sub EXT for external. Now, this is equal to W, and this is the same W as the W in our energy equation, our change in energy equation. And so if I write that delta E sub thermal plus work from the external force is equal to 1/2 kx squared plus 1/2 mv squared. Now, why would I go through all this trouble? Why would I go through all of this to pick apart the work done into a thermal and a effective mechanical work component, and look at the change in energy and plug in all those zeros? Why would I go through all that hassle? Well, the answer is simple. We want to get power is equal to F times V. We need to know V. We know F. That's not terribly difficult to figure out, right? We were kind of even given that at the original problem statement. The force is going to be that tension force of 100 newtons. But V is not so easy to find. And this equation here is what's going to give us that V. So if I subtract a 1/2 kx squared from both sides of this equation, there is something I should mention. The energy, the thermal energy, is going to be a positive. We are going to be increasing the heat of the system by that friction force, right? When you rub two blocks together, two different surfaces together, and you create this friction, you also create heat. This is how you see in the cartoons where they start fires by rubbing two sticks together. When you do that, this external work is being converted into a thermal heat energy, and it's within the system. So it is going to be positive because this delta E sub TH thing is increasing. The other thing we have is our external work. This will also be positive because it is being done on the system. Now, there is an argument that we will make later about the direction of friction and some other things that will cause our E sub thermal to be a negative value. But we'll see that here when it gets. Anyways, I subtract my 1/2 kx squared from both sides. These cancel, and I'm left with 1/2 mv squared on one side of my equation. And on the other side, I get delta E thermal plus work done by the external force minus 1/2 kx squared. Then if I multiply both sides by 2 and divide by m, multiply by 2 and divide by the mass m, I get that V is equal to 2 times delta E thermal plus work external minus 1/2 kx squared. 2 over m. Now V, we have an expression for now. The issue is figuring out what E thermal and the work external are. So we don't really have equations for these things, but they are both a type of work that is being done. And we can calculate them as delta E thermal is equal to the work done by the friction force. That would be friction force, or force, times distance, or delta x in this case, times cosine of the angle between delta x and the friction force. Now, if I were to draw out a free body diagram, I would have a friction force in the negative direction. I would have a tension force in the positive direction. And then my displacement would also be in the positive x direction. I should call that delta x. All right, so my delta x is in the positive direction. My friction force is in the negative direction. And so the angle between them is actually going to be 180 degrees. And so cosine of 180 degrees becomes a -1. So what we get is E thermal is equal to negative friction force times delta x. Again, this friction force is mu k mg, so this is equal to negative mu k mg delta x. If I plug in numbers for those, I get somewhere, I get negative 0.3 times 5 kilograms times 9.8 meters per second squared times our distance delta x of 0.5 meters. And my answer then is about 50 joules. Sorry, no, this is about negative. Issues. Oh, I'll put it up here. This is about equal to negative 7.4 joules. That is our E sub th value. Break that down here as well. All right, then we have this work, this external force work. This is the work that is done by our tension force T. So its calculation will be done by T times delta x times cosine of theta. Here you can see that our tension force and our delta x both point in the same direction, and so this is cosine of 0 degrees. Cosine of 0 degrees is 1, and so we get our work force, or work done by the external force, is just T times delta x, which is 100 newtons. That's the T they gave us in the problem statement, times delta x of 1/2 meter, and the total is 50 joules. This is our work external. From here, I can plug in my values for work external, E, delta E sub thermal, and minus 1/2 kx squared. I would plug them into this equation, and I would get some final velocity. I'm kind of running out of ability to talk here, so I'm going to just briefly brush through this, and I'm sure you can figure out how to do the rest. So we plug in negative 7.4 for E sub thermal, we plug in 50 for WEXT, and then whatever 1/2 kx squared ends up being, we plug that into, we multiply it, we add those together, we multiply all of that by 2 divided by the mass. Again, I think this is a 5 kilogram mass. And, oh, I forgot to we take the square root of this whole thing, because this was b squared, and this is b. So we have to take that square root, and then once we get our velocity v, we could take our velocity v and plug it in here, and so our power, all right, so if I plug in all the values, I get a velocity of somewhere around 3.6 meters per second squared. And then when I take my force, F is 100 times that 3.6, we end up getting something like 360 watts is our solution to that problem. So, thank you for sticking with me. I apologize for being gone these last few days. I have not been in the best of health, and I apologize for if there's any major issues with this video. If there are, let me know. I will come back and try to cut them out and redo them and fix it. So, all right, thank you very much. We will see you next time. Hopefully I will see you on Thursday, and we will probably do just a couple days of review for the final, go over what's going to be on the final, and make some decisions about what kind of problems we'll have. So I will look forward to seeing you then.